Hello everyone. This week we'll be talking about MSTs, or minimum spanning trees. So if we have some graph with some set of vertices and edges, the minimum spanning tree contains all of the vertices, but a subset of edges such that there are no cycles and it's a valid tree. And if you sum up all of the edge weights in the minimum spanning tree, it has minimum total weight. Cool, so let's start off with the light edge property, which is crucial to analyzing minimum spanning trees and developing intuition for algorithms around finding a minimum spanning tree within a graph. So the light edge property states that if we have a graph with a set of vertices and edges, and if we partition the vertices into two sets, so U is a subset of V, and we have all of the remaining vertices in V minus U, then the edge with the minimum weight crossing this partition from U to V minus U must be in the MST. So what does that mean, right? So if we have some graph G over here, and I partition all the vertices into U and U minus V, we have some set of edges that might be crossing this partition. And the light edge property states that the minimum edge must be the MST. So in this case, we have two minimum edges. In this case, we have an edge of 3, 1, 5, and 1. So these two edges are of minimum weight crossing this partition, and one of them must be in the MST. So that's the light edge property. So a short proof of why this is true, we can do this by contradiction. So basically, assume that you picked some other edge that was not of minimum weight, because that's crossing a partition, and you have some minimum spanning tree. Now you can form a contradiction because you can actually make an even smaller spanning tree by just replacing that edge with a minimum weight edge, because now you have an even smaller spanning tree. So that'll contradict your initial minimum spanning tree. So if we have two edges, or two or more edges of the same minimum weight, we can choose either of them arbitrarily, and that won't affect our total MST. So we're going to be talking about Prim's algorithm now. Prim's algorithm is a sequential algorithm, and we're going to see that it has a lot of similarities with Dijkstra's algorithm. So cool, let's get started with a trace on this graph. So we have this graph over here, and we want to run Prim's algorithm to find the minimum spanning tree of this graph. So Prim's algorithm will start at an arbitrary vertex. We know that the MST must contain all vertices, so it doesn't matter what vertex we really start at. So suppose we start at vertex A. Now we're going to exploit the light edge property. So the light edge property states that if you have some partition between the vertices, the minimum edge crossing that partition must exist in your MST. So consider the vertices we've already added. So let me keep track of a visited set. So we're going to visit A right now, and we're going to let this be the partition U, and V minus U will be every other vertex that we have not seen yet. So the minimum edge weight between A and every other vertex in the graph is AB with weight 2. So we're going to add this edge to our minimum spanning tree. Cool. So now with the light edge property, we want to see all the edges reachable from A and B and choose the minimum one among those. So now we're going to visit B, of course. And now there are three possible edges we can choose, right? So there's AD with a length of 3, AC with a length of 3, and BE with a length of 3. So let's suppose we choose AC. So now we've also visited C. And now we want to find the minimum edge weight from A, B, and C to the rest of the graph, and in this case, CE has a length of 1, so we're going to choose this vertex, or this edge, sorry. So we've also visited E. And now the minimum edge will be AD or CD, but we can choose AD. Note that we can't add the edge BE, because B and E are already in the same partition because they've both been visited. So if we add this edge, it's going to really just create a cycle, which is going to break the minimum spanning tree property of being a tree. So thus the only two edges we can choose between were AD and CD, and I chose AD arbitrarily. So we visited D. So now what's the next edge that we can add? So the smallest one is CF with a length of 6. So now we've also visited F. And finally, the only vertex we haven't visited yet is G, so we must add that as well. And the only edge crossing from this partition to G is this edge FG. So now we have a minimum spanning tree, and if we just sum up all of the weights, we will get the value. So there are clearly a lot of similarities between Prim's algorithm and Dijkstra's, in that we're looking at the minimum edge weights whenever we add them. So when you're implementing Prim's algorithm, you're probably going to use a priority queue or some sort of structure that allows you to pick the minimum edge at each round. So we'll go into the implementation next and look at how it's similar to Dijkstra's. Cool, so here's a skeleton code for Prim's. I've left some lines blank, but we're going to fill those in together. So again, so what is Prim's doing? So Prim's at each iteration is going to look for the minimum edge weight from all the vertices that we have visited to all the other vertices in the graph, and then choose that edge, and then add it to our MST, and then continue until we've seen every single vertex in the graph. Cool. So this is the main function, and then this is like the wrapper function, and this is like the actual recursive function that's going to continuously update our priority queue. So this is our initial graph G, and we have three main data structures that we're working with. X is a set of visited vertices, so that we don't look at the same vertex over and over again. T is our minimum spanning tree. So X is just a set, and T is going to be a list of all the edges that we're going to add onto our minimum spanning tree. And Q is a priority queue, just like we saw in Dijkstra's algorithm, and it's just going to store our minimum edge weights. Cool. So in each iteration, we're going to find that minimum edge in that, by the line edge property. So we're going to first case on deleting the minimum element, so popping off our Q. And if our Q is empty, then we can go ahead and return our current MST. Cool. But otherwise, if there is some edge that we want to add to our MST, we come into this case. Cool. So we have some edge and its weight is D, and we have UV is like the actual edge that we're gonna see if we want to add to our MST or not, and Q prime is our new priority queue. Cool. So if we've already seen this vertex X before, then we can just go ahead and go on to the next iteration of the algorithm. So we can run helper of X. We're not going to change our visited set. We're not going to change the tree, or the minimum spanning tree, but we will update our Q to Q prime. Cool. So since we've already seen the vertex V before, if we were to add it to our minimum spanning tree, that would cause a cycle, right? Because we would add an edge within the same partition of the graph. So that's why we want to just move on to the next iteration of the algorithm. Cool. So otherwise, we know that we haven't seen V before, so this is the first time we're going to see V. So we can update our set of visited vertices by unioning it with the vertex V. Cool. And then we also want to update our T based on what this edge is. So we use option types when we're passing in these edges into the priority queue. The reason for this is in the initial case where we pick a root, where we pick an arbitrary root, there is no edge that takes you to the root. So initially we let this edge just be none, comma, some arbitrary root, in this case 0. But otherwise we will always insert some type of options into our priority queue. So if it's a none, we know that that's the root case, so we're not going to add any edges just yet, so we can just return the current T, so like our T prime doesn't change at all. But if it's some valid edge, we know that it has minimum distance, so we can go ahead and add that to our priority queue. So we can add that by just consing on U prime, comma V into our initial MST. Awesome. And now that we've visited this vertex, we want to add all of its out neighbors. We want to add all the out neighbors of V back into the priority queue. So how do we do this? We want to define our relax function, just like we did in Dijkstra's algorithm, by just inserting into our priority queue. We're going to insert into Q prime. And the priority is just going to be the weight of this edge, so W. So sum of V, comma V prime. So note that this is an edge that we can possibly add into our MST, and that's why we use the sum notation over here, because V is a valid vertex in the graph, and then from there we're going to V prime. After all this, we're just going to recurse on helper with our updated vertex set, our updated tree, and our updated priority queue with all the new edges of the neighbor V added in. And when we first call our helper function, we're just going to call it on the empty set for the visited, because we haven't seen anything yet. Our initial MST is going to be empty, and we're going to initialize this with just the root. So there is no edge that takes us to the root, and that's why we use the none notation over here. But we're going to assume that the graph is enumerable, and that this is the root, which is 0. Cool. So let's go through some cost bounds for Prim's algorithm. It's going to be very similar to Dijkstra's because the setup is super similar. The only real difference is that we don't sum up all of the edge weights together. In Dijkstra's, we're keeping track of the running sum of the distance from the source to the current vertex. Here here our priorities are just the raw edge weights themselves. Cool. So we have a priority queue Q, which is our main data structure in this algorithm, and Q can grow up to a size M, where we have M edges in our graph. Inserting and popping into this priority queue is going to be log M with a normal priority queue. So we're going to have at most M iterations, because we're going to pop from this priority queue at most M times, so M iterations. And in each iteration, we're going to do logarithmic work with respect to M, or the number of edges. So we have a total big O of M log N. can write to O. And this simplifies to big O of m log n, because we know that log n is in log n. Cool. So in Dijkstra's algorithm, we saw that if we were searching for the shortest distance from S to T, so S to T, we could actually stop the algorithm early once we see T, because we know that the first time we visit a vertex in Dijkstra's algorithm, that must be the minimum distance from S to T, because of Dijkstra's property. So is there a similar optimization that we can do with Prim's algorithm? Like here we have at most m iterations. Can we stop earlier once we know something about this tree? So we know that a tree, if we have a tree with n vertices, it must contain exactly n minus 1 edges. So we can have an early stopping criteria as just checking the size of this tree. So if we have n minus 1 edges in this tree, we can just stop right away, and we don't need to continue further popping off the priority queue. So note that this algorithm is completely sequential, just like Dijkstra's. We don't exploit any parallelism anywhere. We use iterate, which is sequential. So the span of this algorithm is going to be exactly the same as the work, which is going to be m log n. So now we want to look at some parallel MST algorithms that exploit parallelism. So we're going to look at a fun one. So now that we've seen a sequential algorithm, let's look at a parallel MST algorithm. Today we're going to be learning about
Boruvka's algorithm.
I love the haircut. Where'd you get it?
Where'd I get my haircut? I got my haircut from Anish. Ask Anish for your haircuts. He'll mess it up terribly. So we're going to talk about Boruvka's algorithm now. So Boruvka's algorithm is an algorithm that uses graph contraction and star contraction to contract the graph in parallel while identifying the light edges using the light edge property to build the MST in parallel through contraction. So the general idea for Boruvka's is by the light edge property, we saw that if we had some partition U and V minus U, when we look at the edges across that cut, one of the edges with the lightest weight must be in the partition. So what we do in Boruvka's algorithm is we say one partition is a single vertex. So if I have some single vertex V, and then the rest of the graph is all of the entire graph set minus that single little vertex V. There's edges coming out of this one single vertex here. And whatever the edges might be, I know by the light edge property, the lightest edge coming out of every single vertex must be in the MST. So Boruvka's algorithm kind of exploits this property where I can just look at each individual vertex and see what's the lightest edge coming out of that vertex. I know that that edge must be in the MST. And we call these lightest edges coming out of each individual vertex in the graph, these are called vertex bridges. So the general idea with Boruvka's is that we're first going to identify all of these vertex bridges in the graph. And we'll notice that the set of all vertex bridges, if all of the edge weights are unique, this will form a tree of the graph. Because if they're all unique, then we'll have the unique MST. The vertex bridges will define the MST of the graph. So what we'll do is we'll look at all the vertex bridges in the graph, and we'll use star contraction on these edges. We'll flip coins at each vertex, follow the rules of star contraction, where we have tails for a satellite and heads for a center, contract along the vertex bridges, and every edge that we contract, we add it to the MST. And now we'll have a smaller graph that we can recurse on by doing the same operation, performing star contraction, and repeating until we have no edges remaining in the graph. And all the edges that we contracted along, we know are in the MST, and we're done. Yeah, so the reason why Boruvka's algorithm is parallel is that for each individual vertex in the graph, we can identify its vertex bridge, and we can flip all those coins in parallel to do the contraction. So where with Prim's algorithm, we have this idea of a visited set, where we're slowly building up that visited set round by round and looking for the lightest edge that reaches outside the visited set. With Boruvka's algorithm, we can look at all of the vertices in parallel and find their lightest edges and contract those at the same time, which gives us a parallel speed up. Cool. So let's go through an example now for seeing how Boruvka's works. Okay, so we're going to run the first iteration of Boruvka's algorithm on this graph here. So the first thing we're going to do is for each vertex, we have to identify the light edges in this graph. So for each vertex, we're going to look at the edges coming out of it, and we're going to denote those as the light edges, the vertex bridges for each vertex. So we can start with vertex 1 here, and I can see that we have two edges coming out, 3 and 6. The lightest edge coming out here is this edge 3, and I'm going to denote this light edge with like an arrowhead on it. So I'm going to denote these with blue arrowheads, and why we do this will become apparent when we start doing contraction. So we're just going to do this for each vertex in the graph. So for 2 here, we have 3, 2, 9. So 2 is the vertex bridge. For 3, we have 6, 2, 9. So 2 is the vertex bridge here. For vertex 4, we have 2, 2, 8. And since we have 2 of the same weight, I can pick either of these vertex bridges arbitrarily. So I'm going to pick the one from 3 to 4, and I'm going to label this one here as the vertex bridge. So notice this is a vertex bridge for both vertex 3 and vertex 4. So we have this arrow going both ways along this edge. So for vertex 5 down here, we have 8, 9, and 18. 8 is the lightest edge. That's our vertex bridge. 6, we have 7, 8, 8, 9. So 7 is the lightest. For vertex 7, we have 4, 7, 9. So 4 is our vertex bridge. 8, we have 4, 1, 4. So 1 is our vertex bridge. 9, we have 1, 3, 9. So 1 is our vertex bridge. And finally, we have 10. We have 3, 4, 18. So clearly 3 is the lightest edge, and that's the vertex bridge we have there. And so I did this process sequentially, but notice that this step here is super parallel. I could have calculated the lightest edge, the vertex bridge, for each of these vertices in parallel. So that gives us a massive speed up. So the next thing we can do here is, now that I've defined all of the vertex bridges in our graph, we're going to want to flip coins in all the vertices so we can figure out how we want to do star contraction on these vertex bridges. So we're going to flip coins. So now that we've flipped coins on all of these vertices here, we can now define what edges we want to contract. So we're going to use essentially the same rules we do in star contraction. So we define the satellites as tails and the centers as heads, and we're going to contract along an edge only if it's a vertex bridge in the direction we drew these arrows before. So we're going to contract a tails to the heads where we followed the direction of the vertex bridges we specified before. So notice we have a tails to heads here, but this is not in the direction of the vertex bridge we specified before. But notice from 4 to 3 here, we go from a tail to a head, and we have an arrow indicating a vertex bridge. So that we're definitely going to contract this edge here. That means this edge is in the MST. And we know this because by the light edge property, we marked this earlier as a vertex bridge. So it's going to be in the MST. So what other vertex bridges do we have in this graph that we're going to contract? So we have a tails and a heads here along a vertex bridge this way. Since we have the arrow going this way, we know we're also going to contract this edge in the graph. Let's see what else we have here. So from 7 to 8, we have a tail and a head. So we're going to contract this way along this vertex bridge. And also from 9 to 8, we have a tail and a head, and we have a vertex bridge arrow pointing in this way. So we're going to contract this edge as well. Notice that we also have a tails here and a head here, but we don't contract along this edge because we didn't denote it as a vertex bridge. So now that I've labeled these vertices here, I can start to define some different partitions in our graph after we do this contraction. So notice this vertex doesn't get contracted. So this is one partition all by itself. Same thing here. This is a partition all by itself. But 4 and 3 are contracted together. So this is one big partition. Same with 5 and 6. These two are getting contracted together. And 7, 8, 9 also now form a big partition. And 10 is by itself as its own partition. So now we took this graph of 10 vertices and simplified it down to 1, 2, 3, 4, 5, 6 partitions. So we're going to do the contraction process now, where we're just going to essentially keep the edges and the weights as they were, but we're going to do a relabeling process where we're going to relabel all the vertices and all the edge endpoints by whatever label the center of each partition is. So for the singleton partitions, 1, 2, their vertex labels are going to be the same. 1, 2, 10 are going to exist in our next round. But when we contract 4 into 3, since 3 is our center, all of the edges connected to this partition here will now just be relabeled with an endpoint of 3. So we'll have, like, for example, before we had an edge 2, 4, this is now going to be relabeled in our contracted graph as an edge from 2 to 3. And so on and so forth. For all of these different edges, we're just going to have to relabel the endpoints for our next round. So we're going to go through and do this relabeling, right? Okay, so now we've contracted this entire graph down and taken each of those partitions and contracted them down to a single vertex. So the edges that we contracted along, we've now put those edges in our MST. So those were from the previous iteration, edges 4, 3, 5, 6, 7, 8, 9, 8. We know those edges must be in the MST. And now we've contracted all of our vertices and edges, and we've had to relabel the endpoints of those edges. So for example, this edge 7 with weight 7 here in the previous graph connected vertex 6 to vertex 7. But since 7 was contracted into 8, we now relabel the endpoint 7 with 8, since that's the center of the resulting partition after it's contracted. Similarly, this edge here went from 6 to 9 with weight 9. 9 was also contracted into 8, so we relabel that endpoint. So now both of these edges go from 6 to 8. And note that after we do this contraction process, we kind of have multi-edges in the graph now, right? Since multiple vertices can now connect two partitions, and they might have different weights. These multi-edges don't really matter that much, because if I have two edges connecting partition A to partition B, I can clearly just pick the lighter of the edges. So if you want to simplify things down, you can eliminate the heavier edges, but we'll keep them in for now. So now we can begin the next round of Boruvkas. So we're going to do the same thing again. Let's label all the light edges in the graph. So for 1, we've got edge 3 here. For 2, we have 2, 3, 9. So we have 2 here. 3, we have 6, 2, 8, 9. So for vertex 3, we have edges 6, 2, 8, 9. So this edge 2 is the heaviest edge. For vertex 6, we have 9, 8, 7, 9, 18. So the lightest is this edge here, 17, or edge 7. For 8, we have 9, 7, 9, 3, 4. So the lightest is our 3 here. And finally for 10, we have 3, 4, 18. So the lightest is 3. Cool. So we've now labeled all of our vertex edges, our vertex bridges in the graph, and now the next step in Boruvkas is we're going to flip coins again. Okay, so now we flip coins on this graph here. And now that we flipped our coins, we can figure out what edges we contract using that same rule of tails contract into heads, and we have to contract along a vertex bridge. So notice we have a tails here and a heads here along the vertex bridge pointing this way. So we're going to contract this edge 3 here. We have another tails to heads here along this vertex bridge. So we know we're going to contract the edge 2. And then we have a tails to heads here, but this is not a vertex bridge. But from 8 to 10 here, we have a tails and a heads, and we have a vertex bridge in this direction. So we're going to contract this edge 3 with weight 3 here as well. So these are the only edges we're going to contract in this round, and these 3 edges are going to be in the MST. So let's relabel our partitions again real quick. So 1, 2, 3 now they form a partition. 6 on its own is its own partition. And then 8 and 10 are also going to be their own partition. So we've contracted these 6 vertices now. We're going to contract them down to 3 vertices. And the edges we contract are going to be in the resulting MST. One last nuance of Boruvka's algorithm and these edges we contract is that in later rounds and in later iterations, notice that as the endpoints of these edges get changed around, the edges we contract might be different from the edges in the original graph. So for example, this edge of weight 3 here that we're contracting in this round, right now goes from vertex 8 to vertex 10. But this edge 3 in the original graph originally went from vertex 9 to vertex 10. So we shouldn't say that this is an edge between 8 and 10. This is actually an edge between 9 and 10 in the original graph. And the way we usually get around this to make this efficient so we know what vertices the edges belong to in the original graph is, in addition to the edge weight for each vertex, we also store some metadata about, in the original graph, what were the 2 endpoints u and v for each edge. So that as we contract the graph down, even if the 2 endpoints in the contracted graph change, we still know with each edge what the 2 endpoints were in the original graph, and we can get the MST from that. So now that we've defined our partitions here and the edges we're going to contract, we're going to again contract this graph down, and we're going to do one more iteration. Okay, so we've contracted this graph down, And we have the 3 partitions and the 3 vertices remaining. So the edges we contracted, I've labeled those 3 edges we contracted in the previous round with our original endpoints in the original graph. So we contracted 1, 2, 2, 4, 9, 10. So those are also in our MST. So now we're down to this final graph. We're gonna run one more round of Boruvkas. So for vertex 2, the light edge, we have 9, 8, 9. So we're gonna label that with the edge 8 here. For 10, we have 9, 9, 7, 18. So that's this edge 7 here. For 6, we have a lot of edges. We've got 9, 8, 9, 7, 18. And again, that's also going to be edge 7 here. So now that we've defined our vertex bridges, we're going to flip coins. We're going to flip coins. And now that we've flipped our coins, let's finally figure out what edges we contract. So we have a tail and a head along this vertex bridge here. So we're going to contract the edge here. And then we also have a tails and a heads here along this vertex bridge here, 7. So now that we're going to contract these 2 edges, notice that the entire graph now is just defined by one single partition. So after we contract this graph down, we're just going to have the resulting graph is just going to be a singleton vertex, right? Both of these are going to get contracted into 6. So the resulting graph after this will just be a singleton vertex with no edges, and we know Boruvka's is done. We contract these 2 edges here, 2, 6 and 6, 10, which when we use the original labels of the vertices in the original graph, so those are the edges 6, 7, and 4, 6. And so since those are the last 2 edges we contract, notice that we start with a graph with 10 vertices, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So we have n-1 edges in a resulting graph, and these set of edges here define the MST for our graph. And we have no more edges, no more contraction, so we're done. So we found the MST.
Boruvka!
In Boruvka's algorithm, at each round, we select a set that we call the vertex joiners. Or in the notes, in the textbook, I think we call these vertex bridges. Vertex bridges. And this is the set of minimum weight edges on each vertex. So these bridges, we then add them to the minimum spanning tree, and we use them to contract the graph and continue running Boruvka's algorithm. But there's a subtlety here that we have to be careful about, which is that if the bridges form a cycle, then we've done something wrong. Because clearly a cycle can't be in the minimum spanning tree. Okay, so we'd like to consider, like, when is it possible for a cycle to emerge in this situation? Let's look at a small example. A, B, C with 3 edges, and put X, Y, and Z. Okay. And let's suppose that the vertex bridges, when we run Boruvka's algorithm, actually includes all 3 edges. It includes X, Y, and it includes Z. Is that possible? That's something we'd like to understand. So let's look at, from the perspective of A, it sees 2 edges, X and Z. And let's suppose it chooses X. Okay, so I'm going to draw this arrow, which just means like A chose this edge. If A chose that edge, then X must have been a better choice than Z. So we know that X is less than or equal to Z. Okay. But now from the perspective of B, we have the same sort of situation. So it either selects this edge or it selects that edge. Okay. Well, if it selected X, then we wouldn't have a cycle, right? It must have selected Y. And that means that Y must be better than X. And then finally, from the perspective of C, it sees 2 edges here. We know that it wouldn't select Y because then we wouldn't create a cycle, right? Nobody would have selected Z. So it must have selected Z, and that must mean that Z is less than or equal to Y. Okay, so now we have these constraints on the edge weights. And the question is this possible? Well, at the moment, certainly there's no contradiction because like Z could just be equal to Z and that would be fine. But actually, if we assume that the edge weights are distinct, then we know these can't be equalities. And so then we get a contradiction. We see like, oh, we supposed that we had a cycle, we supposed that we had distinct edge weights, but now we're able to figure out that z is actually smaller than itself. Okay, so this is a proof by contradiction to show that you can't create a cycle if you have distinct edge weights. I've really only done this by showing you a small example, but you can generalize this to larger cycles and larger graphs, right? Because if I have some graph with maybe lots of interesting edges, okay, but maybe I select in my vertex bridges, I select a particular subset of these edges that form a cycle. Let me go ahead and highlight some of them here. So maybe I select these to form a cycle. Well, now what we can do is, once we suppose that we have a cycle, we can kind of observe that it has a direction. When I was drawing those arrows before, based on which vertex was choosing which edge, you can kind of see that the only way it can possibly be a cycle is if they all kind of choose, this has to choose that edge, and this has to choose that edge, and this has to choose that edge. No two vertices can choose the same edge, because then you wouldn't have a cycle, right? Okay, so you can kind of observe that the cycle has a direction to it. And then you can build up these constraints along the cycle, and you can say, well, clearly I'm going to have a contradiction somewhere, because I'm going to eventually figure out that any edge weight is like smaller than itself, because the cycle has to increase or decrease as you go around the cycle.